Hello, welcome to my talk on turbulence models, two-equation turbulence models, Part 2, the enhanced turbulence models. However, when I put the information together, I found it would be too much for one talk. Therefore, I have to separate this part on enhanced turbulence models to two parts, and in this part, the focus would be on the low Reynolds number turbulence models and some simple enhancements on the K-epsilon models, including the Realizable and RNG K-epsilon models. Basically, the two-equation turbulence models are the most popular turbulence models in practical applications, especially for the K-epsilon and the K-omega models. And the two-equation turbulence models is the least turbulence model for the complicated flows, according to Turbulence. However, there are still a lot of limitations for the two-equation turbulence models. The remedies would be for improving the capacities of the turbulence modeling for different and wider applications, including the K-epsilon model is extremely difficult to integrate through the viscous sublayer. Thus, the low Reynolds number turbulence models or the elliptic relaxation would be used. The earlier K-omega model has a strong free stream dependency. Hence, the inclusion of the closed diffusion term would be important. The transition from laminar to turbulence model, which is still very challenging, and the low Reynolds K-omega model is for this purpose. And in here, the great items would be discussed in the second part of the talk on the enhanced turbulence models. And in the talk, some applications would be given. For the low Reynolds number K-epsilon turbulence model, the transport equation for the turbulence kinetic energy, K, for the steady flow is given in this form. This form is very similar to the standard K-epsilon model. And the transport equation for the dissipation rate epsilon can be formulated using the constructed dissipation rate epsilon as this. Here, epsilon 0 is employed to ensure epsilon would not be 0 when y approaching to 0, that is, near the solid wall. And the transport equation for solving the dissipation rate epsilon tilde is given as this. And the kinetic eddy viscosity is calculated by this formula. So from the transport equation for the dissipation rate and the eddy viscosity formulation, we can see this function F1, F2, and F mu, as well as the additional term E for the low Reynolds number K-epsilon model. For the low Reynolds number K-epsilon model, many researchers gave their formulation for the turbulence model. In 1972, Jones and Ronda gave the low Reynolds number as this. Here, F1, F2, F mu are formulated as this, and the epsilon 0 given as this, E given as this. and the closure coefficient are given in here. In 1974, Ronda and Sharma defined the turbulence model given by Jones and Ronda. So the basic form are same. Small adjustment happened for the function mu here, and the coefficient C epsilon 1 and C epsilon 2. Otherwise, they are all same. And in 1981, Nam and Blumhorst proposed there are different no Reynolds number turbulence model. So the function f1, f2, and f mu are given as this. But here, epsilon 0 and E are both 0. The closure coefficient given here. And in 1982, Chen used the similar idea to the Jones-Ronda model, so defined the function and the coefficient. So the functions and the closure coefficient are given in here. So in this slide, the realizable K-epsilon model is introduced. The realized K-epsilon model is an enhanced K-epsilon model with a new transport equation for the dissipation rate and realizable eddy viscosity formulation. Thus, the model is called Realizable K-epsilon model. The transport equation for the turbulent kinetic energy is exact same as the standard K-epsilon model given as this. And the transport equation for the dissipation rate epsilon is given as this. Here, the equation is based on the mean square vorticity fluctuation at large turbulent Reynolds number. And the kinematic eddy viscosity is calculated using the same formula as that in standard K-epsilon model, but the coefficient C mu is not a constant. The closure coefficients and the functions are given here C1, C2, sigma k, and sigma epsilon. The closure function for the coefficient C mu given in this formula. Here, A0 is 4.04, and the AS given by this function, with phi given by this, and the W calculated this as tilde is calculated as this. And the U star is given by this. Here, omega tilde ij is calculated in this formula. In this slide, the statistical technology called the renormalization group RNG theory is employed for studying the hydrodynamic model, and this statistical technique is used on the Navier-Stokes equation directly and derive the relevant equations and the important constants for the turbulence flows. So the transport equation is the RNG theory is given as this. Here, the turbulent Prandtl number alpha k can be calculated from this algebraic relation. And the transport equation for the dissipation rate epsilon is given in this form. And again, the effective Prandtl number alpha epsilon can be calculated in this formula. And in this transport equation, we can see the additional term R epsilon. The effective viscosity mu EFF can be solved from the equation as this, and mu hat is calculated as mu EFF divided by mu. And here CV is given as 100. And the additional term in the transport equation for the dissipation rate, R epsilon, is given in this formula. Here, eta is given, this eta 0 is a constant, and beta constant. And the closure coefficients for the RNG K-epsilon model are actually 2, C1 epsilon and C2 epsilon given here. Generally, the K-omega model has no difficulties in integrating through the viscous sublayer. Thus, the low Reynolds number K-omega model is not common. However, the low Reynolds K-omega model has been proposed, but it is more on tackling the modeling of the flow transition from laminar to turbulent, since the conventional K-omega model tends to predict the transition at a much lower Reynolds number, which is 8,100, compared to the real Reynolds number, 90,000. The transport equation for a steady flow past a flat plate. The transport equation for the kinetic energy K is given in this form, and the transport equation for the frequency omega is given as this. These two transport equations are basically different from the conventional K-omega turbulence model. The function alpha star here and here. And the kinetic eddy viscosity is calculated as in this formula. Again, we can see alpha star is used here, and the limiter of the omega tiered, is given in this form. So the closure coefficient and the functions for the low Reynolds number K-omega model, we have 11 closure coefficients against 6, and the functions, the low Reynolds number K-omega model has 5 functions compared to 2 functions. So here we can see alpha star given in this formula and alpha beta star. In a similar way, there's a blending function for the low Reynolds number K-omega turbulence model, sigma d given as this. So in this slide, a discussion will be made for the near-wall treatment. So in the past, numerous Y plus insensitive wall treatments have been proposed, mainly for the K-epsilon turbulence models, which can be used to avoid the stringent grid resolution requirement of the viscous sublayer models, and to ensure that the predicted wall shear stress and the heat transfer are independent of the near wall resolution. So the common remedies are those low Reynolds number turbulence models, or use Doben's elliptic relaxation model, which is implemented in his K-epsilon V squared model, published in 1995. For K-omega model, however, it has been shown that the K-omega model has a built-in elliptic relaxation, since when we look at the transport equation for the omega, we can see when y approaching to 0, the omega equation would reduce to this form. This equation where represents the flow in the near wall region without a need for additional transport equations or damping functions. Thus, this feature makes the omega equation a highly attractive and robust turbulence model. And this feature may be the main reason why the K-omega model has been so successful, and also the SST K-omega model has proven good accuracy for a wide range of the heat transfer test cases. So in this slide, an application for the low Reynolds number turbulence model. The test case is the Samuel and Jobert's adverse pressure flow. From this figure, we can see the experimental data is quite close to the theoretical formulation given by this, but the Lambda and Sharma model give the result a little bit far away from the experimental data. Obviously, the Lambda-Sharma model can't predict the constant. Also, in the reference below, for the test case of 12 incompressible boundary layers with adverse pressure gradient, and for the skin fraction CF, the average difference between the computation and the measurement for the 12 cases are 6% for the K-omega model, 43% for the Jones-Round model, and 47% for the Lambda-Sharma model, 46% for the Chen's model, and 58% for the non-Braunhorst model. If you like to see more details in the comparison, please refer to Wilcox's book. The second application is for the comparison of the separation bulb length for this test case, separation bulb here. In this table, it is shown for the prediction of the separation bulb length ratio delta x divided by d using different turbulence models, including algebraic, half equation, one equation, K-epsilon, K-omega, and K-epsilon model. So the best case in this table is the Wilcox K-epsilon model 2006 version. And the worst case is the prediction from the K-epsilon model, since the Lambda-Sharma's K-epsilon model didn't predict the separation at all. And it is also interesting to note the half equation model gives a very good prediction for the separation bulb length in this case. Now in this slide, the concluding remarks would be given. Generally, low Reynolds number collection increases the complexity of two equation models significantly. For instance, the high Reynolds K-omega model has just 6 closure coefficients and 2 closure functions, while the low Reynolds number version would have 11 closure coefficients and 5 closure functions. For the K-epsilon model, the complexity is increased similarly. For instance, the Lambda-Sharma model has 9 closure coefficients against the 5 for the standard K-epsilon model, and 4 closure functions against the 0 closure functions in the standard K-epsilon model. This much increased the complexity of the turbulence model could only be a severe problem if the turbulence model needs to be fine-tuned for some specific applications. In using the different turbulence model, if viscous effects are insignificant for a given application, for instance, away from the wall boundaries, it is advisable to use the simpler high Reynolds number version of the model. In the case of the K-epsilon model, if the integration is needed through the viscous sublayer, the low Reynolds number K-epsilon model must be used. And for the K-omega model, integration through the sublayer can be done without introduced viscous correction. And there is virtually no difference in the predicted skin fraction and the velocity profile with or without viscous correction for the turbulent boundary layer.